can serve as a natural modeling language, and scientists and engineers investigate input-output systems, which transform given input parameters into output parameters. Input-output systems generate, usually in engineering research, numerical data, which can be processed in mathematical terms. Moreover, regarding a mathematical model is a triplet where S is a system, Q is a questions related to this system, and M is a set of mathematical statements which can be used to answer the question Q to this system S. We often use for mathematics with the purpose to model of experimental data, often software programs. With these software programs, we don't need to be professional mathematicians, and the formulation of a mathematical model can be clearly separated from the solution by involving a model. And examples of software for statistics are the OpenOffice Calc, the Microsoft Excel, R, statistic software which is also open source, MATLAB and Mode, which are proprietary software. In scientific research, we often deal with measure, numerical and experimental data. In order to get insight of this data, statistic methods are required. And there are available three main branches of statistics commonly used to process experimental data of engineering studies. We have, first of all, descriptive statistic, inferential statistic, and we have also a third branch, which is called design of experiments. And we are going to see each branch of statistics, what it is about, as introduction to our design of experiments. We have here, for instance, some experimental data within a research of technical textiles. And as you can see on this slide, we have treated fabrics in plasma for different times of period. And we have here treatment for 10 minutes, for 20 minutes, for 30 minutes, and for 90 minutes of plasma treatment. And as you can see on this table, we measured afterwards the tensile strength of the fabrics in what direction? In Newton. This is expressed in Newton. And we have here this measured experimental data, which we can further process. As you can see, the tensile strength of the hydrophobic treated fabrics had the best value at 30 minutes. And with the descriptive statistic, we have several tools to of Pearson. Moreover, we have also inferential statistics, and here we have as example interval the t-test or ANOVA computing, bivariate regression, and multivariate regression. We are going to present you now another important branch of statistics and processing of experimental data, which is called design of experiments. This is the main topic of our today's lecture, and we have done this introduction in order you to see how in order to frame a little bit this big domain of statistics for experimental data. And why do we use design of experiments? Why do we need this extensive field of statistics for processing experimental data? Well, this field of statistics is used to reduce the number of physical experimental runs and get a maximum insight on the experimental data. And we have as examples the Latin square, factorial plans, central composite design, and Taguchi experimental data. And we will see that we will tackle today two types of experimental plans. This is the factorial plans and the central composite design plans, which are usually used for engineering research. Well, once again, two reasons, two rationale for using design of experiments. We can state the fact that if we have for an experiment two significant parameters such as M and N, we must develop M and goal with experiments to reduce the number of mental runs. And also the processing of design of experiments allows us to compute the interconnection between the input parameters. As such, design of experiments establishes values of the input parameters of an experiment according to specific rules. Now we will jump to an example because as you have already acknowledged, our modules are conceived in a problem-based learning approach, and we are going to tackle each type of experimental plan by an example. First example is the plasma treatment of hydrophobic functionalization of fabrics. And we have for this process, so first of all, we'd like to have technical textiles with hydrophobic functionalities. And in order to manufacture these technical textiles, we would like to treat them in plasma. For this purpose, the plasma treating process has two main parts. The variable is the power of the plasma generator, and the second parameter is the process time. You can see here on the right part of the screen the display of the plasma installation, and you can see the various parameters, the temperature, the pressure, and the process time in the down part. Moreover, in order to assess, to compute the hydrophobic functionality of the resulted fabrics, we use the water contact angle. The water contact angle is measured by a goniometer. This is a measurement device which measures the angle by the droplet of water on the fabric surface. If this droplet of water has a high angle, this means the fabric is hydrophobic. So if the droplet of water stays very well with a good angle on the fabric, it means it's hydrophobic. Otherwise, if the droplet is absorbed by the fabric, or if the angle is low, this means the fabric is hydrophilic. And we have for the two parameters, for the two input parameters, several variation levels. We have for the power 3 values. This means 10 watt, 20 watt, and 30 watt. And for the time, we have also 3 values, 2 minutes, 3 minutes, and 4 minutes. As you can see on this slide, the delta is the difference of variation between these levels. For power, it is 10 watts is the difference between the variation of the 3 values of the parameter. And for the time, it is 1 minute. Now, how can we select the values of our input parameters? For this purpose, we have to firstly run some preliminary experimental runs and to see the range of variation in which these experimental results are going. And afterwards, we select the appropriate values for input parameters. And there is also some scientific methods to select these input parameters according to some screening methods. Now, coming back to the previous slide of variation levels, we have to encode the variables power and time according to this general expression, which states that this parameter is going to subtract the mean values or the middle value of the parameter divided by delta, which is the difference between variation levels. If we come back 2 slides, we can see that in our case, delta is 10 for the power parameter, and delta is 1 for the time parameter, and the difference between the variation levels and the mean value of is 20 watt for power and 3 minutes for time. And as such, we have this encoding of the variables, power minus 20 per 10 and time minus 3 per 1 minute. And we would like to propose for modeling this process of plasma treatment, a polynomial equation second degree, which has this expression in the bottom part of the slide, where x is the encoded variable for power and y is the encoded variable for time. And further on, we have to build an experimental matrix for our encoded variables power and time. On this slide, you can see that we have this encoded variable x and y, and we have all combinations between the 3 levels of variation, namely 1, 0, and minus 1. On this slide, you can see that we have here the values for the encoded variable of time, y, and here we have this multiplication coefficients, which means the x multiplied by y, x squared, y squared, and on the last column, for butter contact angle measured with our goniometer on the hydrophobic fabrics. It is simple to observe that for such an experimental matrix at factorial planes, the number of experimental runs is n equals to p at power k, where n is the number of experimental runs, p is the number of variation levels, and k is the number of input parameters. Well, in our case, we have 2 input parameters and 3 variation levels. This means 3 at the power 2, 9 experimental runs. Well, next step, in order to compute our model, is to copy-paste the values of the experimental matrix within Excel. And we have introduced this data of the experimental matrix in Excel. And then we have used data analysis from tab data. And for this purpose, we have also installed the data analysis add-on from Excel, which is a special add-on which has to be installed in order to get this feature of data analysis in the data tab. And from this data analysis option, we select regression, and it opens this window, this dialog window, in which we have to introduce at X range these values with of the experimental matrix with 1 and 0 and -1, and then in the Y range we have to introduce the result variable, which are the values of the contact angle. Afterwards, the software computes the coefficients of the polynomial equation with encoded variables, and we have here these coefficients for our equation, and it results, this equation stated on this right part of the slide, with the intercept value of 134.13 and so on, with all coefficients of the polynomial with encoded variables. Afterwards, we have to decode the coefficients of the polynomial equation we have obtained by using the encoded values of our variables. And if you remember from 3 slides before, we have for X this expression, and for Y the other expression. And now we have to compute, we have to introduce in the Z for Z, these values, X equals with P minus 20 per 10 and Y T minus 3. And after computing once again the coefficients of the polynomial, we get these polynomial equations for the water contact angle, depending directly on the 2 parameters, power and time. As you can see on this slide, we have get this equation related to the 2 parameters, power and time, according to the coefficients computed by the regression analysis. And afterwards, we have plotted this equation, this polynomial equation second degree. We have plotted it in MATLAB, and you can see on this slide the plot regarding the parameter power and time, and here on the Z-axis, the water contact angle. Now, another important issue is to the min-max points of the polynomial equation, which stands for optimizing this process of plasma treatment. And we can get these min-max points by computing the gradient of this polynomial equation, which means the partial derivatives of this expression of the water contact angle polynomial. If we compute these partial equations, partial derivatives, we get an equation system with 2 equations and 2 unknown variables, P and T. And we can compute a solution which is 25.3 watts and 5.03 minutes for the optimal water contact angle value of 137.72 degrees. Now we can perform also other computation related to the variation of the individual parameters of this research experimental design with plasma. And we have here the same equation, but for the time we set the mean value of 3 minutes. And by introducing this mean value of 3 minutes, we get this equation for the parameter of power, which is depicted by this graphic in the left part of the slide. And we can also compute the variation of the individual parameters time by introducing the mean power in the water contact angle equation. And then we receive this second degree polynomial equation, which is plotted here on the left part on the slide. Well, regarding the insight we can obtained by this design of experiment with factorial plans, we have an, by increasing the parameter power, we have seen on the previous slide that the water contact angle is increasing too. So with increase of the power, water contact angle increases too. On the other hand, the parameter time has a maximum value at the time of 5 minutes. And last but not least, in order to get this insight, there was needed only 9 experimental runs we have to develop with our plasma installation. Now, at this moment, I would kindly ask you for any questions up to this first part. So are there any questions? Should I come back to explain any details of this computation? Well, if not, I will go further. You can either put your questions now on the chat. You can also put your questions in the forum of the e-learning platform at the upper part of the communication e-learning. And now I'm going to move forward to the next example. And I will present you another example. However, this time not with hydrophobic fabrics, but with electrically conductive fabrics. So, our aim in this research was to develop electroconductive fabrics for electromagnetic shielding. And for this purpose, we have developed and manufactured fabrics. And we have also coated these fabrics by magnetron plasma treatment. You can see on this picture can you see my my slides? Yes. You can see on this picture the magnetron plasma equipment of our colleagues from the National Institute for Laser Plasma and Radiation Physics. And our aim was to develop these electroconductive fabrics and to measure the electromagnetic shielding effectiveness, which is defined as power of the incident signal, the ratio to the power of the transmitted signal of an electromagnetic wave for a certain frequency. This electromagnetic shielding effectiveness is measured via a transverse electric magnetic cell according to a certain standard. And we have here on this picture this schematic representation of the electromagnetic TEM cell, in which we have to manufacture a conductive, electrically conductive textile fabric, which has this shape, this circle shape, this, yes, and then this textile fabrics is introduced into the TEM cell, which you can see here on the right part of the screen. And as such, we can measure the electromagnetic shielding effectiveness, which measures the, as said, the ratio between the signal with the sample and without the sample. And by taking this ratio, we can see how much our textile fabric shields the electromagnetic field. Well, however, we have used for our second example, not factorial plans, but another experimental design plan, which is called central composite design. And for our central composite design, we have applied two parameters, namely a parameter depending on the textile fabric structure, which is the fabric density, and another parameter, which is depending on the magnetron plasma coating, which is the layer thickness in nanometer. So we have the possibility to coat, to render to this fabric surface a nanometer thick layer, which gives to this fabric electroconductive properties. And we have assumed that with lower fabric density, this copper ions, because there was a magnetron plasma coating with copper raw material, which is very good electric conductive. As the fabric density is lower, we have better penetration of the copper particles between the fabric structure, and we have a better shielding effectiveness. And we, in our research, we would like to analyze these properties of electromagnetic shielding effectiveness and of electrical conductivity, depending on these two parameters, the fabric density, which is expressed as number of yarns per 10 centimeters, and the thickness layer of copper coated on the fabric surface, which is expressed in nanometers. However, in this experimental design plan, we had not only 3 levels of variation, but we have 5 levels of variation. As you can see on this table, we have also the mean value depicted and encoded with 0, the upper value, which is encoded with +1, the lower value, which is encoded with -1, but we have also 2 star points, which are encoded for plus square of 2 and minus square of 2. And we will further see what the theory behind this central composite design plans is. So next step, as in the previous example, was to encode these variables of fabric density and layer thickness. You can see in these two equations, 8 and 9, that we have used the same formula, the same relation to encode the variables, namely the variable minus the medium value um, up to the, so divided by the delta, which is the difference between the medium and upper value. And we have then these two encoded variables, x and y, and we have, as said, 5 variation levels for density and thickness. And then you can see in this experimental matrix that we have at this time 13 experimental runs. Why? Because we have, first of all, for x, these values, minus 1, 1, minus 1, 1, minus square of 2 and plus square of 2, 0. And then we also have 5 replication points of 0. We'll see later on what this replication points are. However, these replication points ensure good repeatability of our experimental research. Now, you can see that in our experimental matrix with encoded variables, we have also this variation of indices, which are, first of all, for x, for y, then for x multiplied by y. And you can see here that minus 1 multiplied with minus 1 is 1. Then we have square x and square y. And you can see that, for instance, minus square 2 multiplied by 0 is 0. Minus square 2 to the power 2, so is 2. And 0 at the power 2 is 0. So this experimental matrix is computed for the coefficients of the polynomial equation. And on the last column, you can see the result variable, which is the electromagnetic shielding effectiveness expressed in decibel. So we can see once again this device, this stem cell for measuring the electromagnetic shielding effectiveness, and this relation of the power of the incident signal divided by the power of the transmitted signal expressed in decibel. We coming back to the experimental matrix, and as such we have this table with all the values, and now we are going also to compute the regression coefficients in Excel. And but before of that, I would like to tell you more on the theory of the central composite design, which is also named Box-Wilson experimental plan after the name of the authors. It is a popular experimental plan, which is mainly used in engineering research due to the fact that it allows optimization of the input parameters and non-linear evolution of the response with experimental domain. There are several types of central composite designs. The one of the types of experimental composite design is the circumscribed central composite design. The second is the face centers. And the third is the inscribed central composite design. And you can see here on this picture how the variation levels are set for all these three types of composite design plans. So for the circumscribed experimental composite design plan, we have, besides the -1 and +1 and these points on this square, we have also star points in which we include 0 and square of 2, 0 and minus square of 2, and also this minus square of 2, 0 and plus square 2 and 0. So we have in the composite design plan more points for experimental data we have further on to run. You can see here on this picture further on the face-centered and described central composite design plans, which vary a little bit regarding these points of the experimental matrix. Then, here is the theoretical experimental matrix for the circumscribed central composite design, in which you can see that we have, for instance, for the fabric density, these values, -1, 1 and minus square of 2 plus square of 2 and 5 points of 0. And we have also for the layer thickness, also the same values, but combined in all combinations. And we have chosen for our model also polynomial equation with 6 coefficients. However, we have used for our computation this time a software which is called MODE. This software is not open source, so it is proprietary. And we have to use this software to get these results of this summary of fit, which are statistic indicators. And we also get this response contour plot of the electromagnetic shielding effectiveness. We also get this response surface plot, which is a plot showing the evolution of the electromagnetic shielding effectiveness depending on the yarn density and the fabric density and of the coating thickness. And the software tells us that we have this maximal value of electromagnetic shielding effectiveness for a density, fabric density of minus 0.021 and a thickness for the value of 1.147. However, these are results of the regression computing. And in order to get the real values of the fabric density and of the plasma coating thickness, we have also to decode our variables. And as you remember, we have encoded our variables, fabric thickness and coating, fabric density and coating thickness, by these two relations, namely the mean value and the delta. And now we are decoding our variables, and we, after the computations, we get these values of maximal electromagnetic shielding effectiveness for 260 yarns per 10 centimeters, and the plasma coating thickness for 1830 nanometers. Well, so this procedure, this practice of experimental design has supported us in our research to see, first of all, what is polynomial equation for this experimental treatment, and to get the optimal values for the maximum shielding effect. This is, as said, 260 yards per 10 centimeters and 1830 nanometers thickness of plasma. Now, if you have any questions up to now, I know it is afternoon. I know there are a lot of mathematical computations. I have to tell you that this is statistical methods for designing of experiments. Now, please be so kind to tell if you have any need of clarifications. So, have you up to now encountered such need to use experimental plans? Did you are some of you are PhD students, and in PhD it is usual to apply such experimental plans for various engineering experimental data. Did you encounter already such experimental plans? I'm asking now all students, especially the PhD students. Well, if you haven't encountered such statistical methods, then I will propose to you to read a little bit the module on the e-learning platform, on the Moodle e-learning platform, to provide us some questions for the morning session planned for tomorrow morning on Wednesday at 9 o'clock Central European time. And then at this session, we could make some practical exercises on how to encode the variables for an experimental process, how to decode them, and how to compute these coefficients of the polynomial equations based off the regression computing in Excel. So, with your permission, I will stop now this presentation. Please be so kind to read the two first examples from this Moodle platform. You all have access to the Moodle platform, and this is Module 5, Research with Experimental Design. Please read the modules and provide us up to tomorrow morning with some dedicated questions on the content, on the educational content. I see Benny on the screen. Benny, would you like to add something on this module, how we should proceed with this module? What do you think?
You hear me? Yes?
Yes, yes, yes.
For the GAN people, I don't think the people present have used design of experiments. So to use data that you have prepared or share, it would be best, I think, and to do tests with
Yes.
that.
Well, then, if not, I suggest this afternoon you familiarize a little bit with this design of experiments content. I know this is something new. I have dropped directly to some examples. Perhaps it is better to take it more slowly, to try to understand the context of the design of experiments, and afterwards, tomorrow morning, we make some more examples regarding practical computations on decoding and encoding variables of polygons. Well, I hope you have enjoyed this session. And with your permission, I will I will invite you tomorrow morning to make these practical examples. So this is all up to now. And I would like to thank you for participating to this course. I hope it was not too difficult. And let's meet tomorrow at 9 o'clock Central European Time to make some more practical examples. All right then. So this is everything for today. Many thanks.